We continue with section 2.6, and you will notice that so far in the examples that we have looked at, we have considered a case where the degree of P is less than the degree of Q, right? And now we are going to do more to be able to have any kind of rational function. So a partial fraction decomposition for a rational function given by f of x is equal to p of x over q of x, where x is a real number such that q of x is not equal to 0, exists only when the degree of p is less than the degree of q, or r of x is equal to 0. We are going to talk about what r of x represents in this case. Right. So, however, if the degree of P is greater than or equal to the degree of Q, then there exist unique polynomial functions u and r such that P of x is equal to Q of x times u of x plus r of x. So the r of x that is being talked about here is that remainder there, right? And the degree of r is less than the degree of Q. And this, if you want to verify this will come much later in the module. So that's theorem 7.2.2. And in this case, we can then write f of x, which is p of x over q of x, as u of x. So if we divide by q of x here, we can see that we will be left with q of x, u of x plus r of x over q of x, where x is a real number such that q of x is not equal to 0. And how do we manage to get this? So the polynomial functions u and r are determined using long division. So we will do long division of polynomial functions. And a partial fraction decomposition can now be determined for r of x over q of x. So because for u of x is just a polynomial, we just integrate it the way we do normally, and then the last part here is what we then need to determine using partial fraction decomposition, right? So for example, we've got example 2.6.7 in the textbook. So we evaluate the integral. So we are given an integral where the degree of the numerator is 4 and the degree of the denominator is 2, right? So that means that we need to do this long division, right? So so let p of x be equal to x to the 4 minus x to the 3 plus 4x minus 2, and q of x be equal to that. And note that the degree of p has degree 4 and q has degree 2. So we therefore perform long division to find polynomial functions u and r such that we have this, right, where x for all x real numbers and q of x not equal to 0. So if we do the long division here, we will see that the u of x will be equal to x squared, and the r of x will be equal to 4x minus 2. How do we do the long division? So we start off with so we can see that we've got 3x squared here, and then there we've got 3x to the 4. So if we divide this 2, we see that we get x squared, and then we take so we put the x squared here, we multiply it on this side, and we get 3x to the 4, which is here, plus minus x cubed, like that. So we multiply that to get that, and then we subtract, right? So that's why we've got minus there and a plus there. We would have multiplied by that to get positive 3x to the 4 minus x cubed, but we have to subtract that from this, right? and if we do that subtraction we will be left with, so that will just give us 0 0, and therefore we are left with 4x minus 2. Now this has degree that is less than the degree of this function or this polynomial is 1, and that is 2, so therefore we have achieved what we want, right? So p of x over q of x can then be written as qx squared plus 4x minus 2 over 3x squared minus x, which can be written as that, and we have to have the condition that q of x is not equal to 0, so therefore that means x cannot be equal to 0 and x cannot be equal to 1/3, right? So so what it means is, from our theorem, there exist unique real numbers a and b, so that a over x plus b over 3x minus 1 will be equal to that. So here we can see that x appears once in the denominator, 3x minus 1 appears once in the denominator, so that is fine. And then if we put this under one denominator, we get that, we get that. So, and then if we rearrange, we end up with that, right? And so therefore 4x minus 2 over 3x squared minus x is equal to a over x plus b over 3x minus 1 if and only if 4x minus 2 is equal to 3a plus bx minus a. And then we create our system of linear equations. We find a and b, and a is equal to 2, b is equal to minus 2, and so therefore uh, that rational function becomes that when we replace a and b with the values that we found. And so therefore this integral becomes x squared, don't forget the x squared that we got in the first place, plus these two rational functions, and then we can easily integrate this, right? So this is one example. You can do example 2.6.8 in the textbook for more illustration of this idea. So we end this section by stating, for the sake of completeness, the general result on partial fraction of a rational function. As you can see, we're dealing with the rational functions where the numerator is degree 3 or maybe 4, and then the denominator also is not too is degree that is not too large. So now we are just going to have a theorem that tells us what we are supposed to do in general, right? In a general case, and that's theorem 2.6.9, and it says, let p and q be polynomial functions on R. Assume that the following is true. The first thing is the degree of p is strictly less than that of q, and q has degree at least 1, right? And if it's not, so the idea here is if it's not strictly less, then we can always do the decomposition or we can do the long division rather, right? And then number 2, the polynomial function q can be written as the product of powers of distinct linear and quadratic terms. So it can be written in this form, where we've got 8x plus 1, so we've got the linear functions here, and then the quadratic functions in that way, where all these numbers are integers, right, greater than 0. The powers are greater or equal to 0, and all the other coefficients, b1, bi's, ci's, cj's, and dj's are real numbers, and ej's are real numbers, and such that ai is not equal to 0, and so dj squared minus 4 cj ej is less than 0 for all I and j that we have. Then for every I from 1 up to k, there exist unique real numbers ai1 up to ai ni, and for every j from 1 up to r, there exist unique real numbers of that form and that form, such that we can write p over x as a sum of these kind of functions. So you can see that once we start dealing with bigger or degrees that are much bigger than the 3's and the 4's that we were dealing with, the situation gets a bit more complicated. And the proof is we don't have a proof for this module. It's beyond this module. Thank you. We will continue with chapter 3. Thank you.